All right, welcome to 9.3, Hypothesis Tests for a Population Mean, now with sigma unknown. Again, we're going to jump right in with a full example. So page 456, number 16, the mean annual tuition and fees for a sample of 14 private colleges in California was $37,900 with a standard deviation of $7,200. Assume the population of tuition and fees from all such colleges is normally distributed. Can we conclude that the mean tuition and fees from all private colleges in California differs from 35,000? Use alpha equals 0.01. So I'm going to read that again and mark a few things, just learning how to read a problem and identify information. So we've got a mean from a sample of 14 private colleges. So we've got our sample of 14, so that's our n equal 14. And because we're talking about this sample, the sample mean, right here, that 37,900, that's got to be our x bar. And then notice that the sentence continues. The mean of this sample was 37,900, and the standard deviation of the sample was 7,200. So that 7,200 is S, a sample standard deviation. Okay. And then assume the population of tuition and fees from all such colleges is normally distributed. Do you know why that's in there, that normally distributed? That's because we have our small sample size, so that allows us to proceed. And then here's our question. Can we conclude that the mean tuition and fees from all private colleges differs from 35,000? All right. And then this alpha stuff, that's our significance level. All right. That's going to help us determine how do we decide significance level. How do we decide if our sample is unusual enough? That's the significance level. All right, so the first step is to write the hypotheses. And if you remember, that's where we write a null hypothesis, and we're talking about means here. So either the mean really is the mean of 35,000 that's proposed for all college, or the language in there with the differs, that's where we use a not equal to symbol. It doesn't say greater than, doesn't say less than, it simply says differs from. So that's our hypotheses, and if you're thinking ahead, that not equal sign does mean that we're going to be doing a two-tailed test. So we'll see how that comes out. Step number 2, the distribution. Since this is a test about means where the population standard deviation is unknown, we use the t-distribution, just like in chapter 8. The alternative hypothesis contains a not equal sign. Oh, and I've already said this, so it is a two-tailed test. We will reject H0, the null, if our test statistic falls in either tail. All right, so let's draw a picture of that. Here's our t-distribution. Looks just like a normal, but now I'm calling it t. 0 in the middle. With confidence intervals, we knew the amount in the middle, 99%, 95%, whatever. Now that significance level, alpha, is the amount that, in this case, gets divided between the two tails. Alpha is always the tail amount, whether it's one tail or two. It's the total amount. So 0.01 in both tails, total. And so we do that same alpha over 2 stuff that we're familiar with, 0.01 over 2 and 0.001 over 2, because it is a two-tailed test. And that's the only time you do that for two-tailed tests. All right, so we need to find the corresponding critical values, because that's what we'll compare our test statistic with once we get that. So remember, there's the two critical values, t alpha over 2, and a negative t alpha over 2. And so either you're going to go to inverse t, if you've got it, with that 0.005 tail area. And then do you remember what goes next? That second number is the degrees of freedom. And that is n minus 1. So our sample size was 14, so we're going to put a 13 in there. And if you use the t-table, you have a choice of looking up 0.01 in two tails or the 0.005 in one tail. And either way, we get the positive version of our critical value to be about 3.012. And so we have the positive version and also the negative version. When we redraw our picture in our comparison step, I'll put them both in there. Okay, that's our critical value. I'll say plus and minus on those. Don't say critical values. All right, so now we're to the calculation step where we're going to put our sample information into the calculator. So we're going to use stat, tests, and then notice it's a t-test because we're working with the t-distribution. So we had our null hypothesis. Okay, from the null hypothesis, we had that mu0, the null, is 35,000. Don't need the comma. Our sample mean was 37,900. That is different from 35,000, but is it significantly different? Our standard deviation was 7,200, and our sample size was 14. So we put all that in there. And over here on the right, if you're curious, if you want to try to do this test statistic by hand, I've given you the formula over on the right. We have all the parts. That would be mu0 up on the top. We have our x bar, our s, and our n. So give it a try if you want to, but absolutely no requirement to do so. But then we have to put in the last line into the calculator. Remember, this was a differs from question, so you're going to choose the not equal to symbol. That's the key, is looking for the correct symbol. And that's saying that in the alternative hypothesis, the mean was not equal to 35,000. All right, put all that stuff in your calculator and press calculate. And up at the top, my calculator reminds me I did a t-test and that my alternative hypothesis was the mean not equal to 35,000. And the first number after that is the test statistic, t, which I'd like you to write down a label. And I get 1.507, rounded to 3 places. And the next number, the p-value, which again, it's really a good idea to label it as p-value rather than just p, because that means other stuff. And I get 0.1557. So we're going to take those two numbers and compare each of them. The test statistic is a value like a critical value. So those are things we compare in a picture on a number line. And the p-value is an area. It's something that we can compare to the significance level, which is also an area. So we're really just doing the same kind of comparison in two different ways. So in the first method right here, the critical value method, that's where we draw our picture. And it doesn't have to be as detailed. All I really care about were those two critical values. So 3.012 and negative 3.012. Those set up my two tail areas, because it's a two-tail test, the two tail areas where we will reject H0. If our sample lands out there, either high or low, then it becomes so unusual that we have to question the original assumption of 35,000. All right, so I'm going to go get my test statistic. That was 1.507. It's positive, but only there. It doesn't fall anywhere past 3.012. So that's our test statistic. So I can see from my picture, I'm going to fail to reject the null. And when we do our comparison of the p-value to the significance level, alpha, the p-value was pretty high, 0.1557 compared to 0.01, pretty small significance level. The p-value is definitely greater than the significance level. So the p-value is not low, the null does not go, and so in both cases, we fail to reject the null. You always want to say something about the null. And then we try to say something about the alternative, the thing we were trying to really test. So acknowledge that we were at the 0.01 level of significance, because a different choice for that would change those critical values, could change our conclusion. And in this case, there is not sufficient evidence to conclude that the mean tuition and fees for all California private colleges differs from 35,000. And there we did it. With a lot of explanation, it took us 10 minutes.